Ladies and gentlemen, good afternoon. Let's continue with chapter 4 in the textbook of Cengel and Ghajar. We've completed paragraphs 4.1, 4.2, and 4.3. 4.1 was on the lump system approach. 4.2 was on transient heat conduction in large plane walls, long cylinders, and spheres. And I said we've completed the first three. That's not true. We are going to finish the third part today, which is transient heat conduction in semi-infinite solids. So just going back to the previous lecture. With the previous lecture, one of you did pick up that I did make a mistake here with this temperature ratio. It is indeed, it should be 0.294. And if you go and recalculate tau, I think it should be equal to 0.5923 then, and then the number of hours or the number of seconds is going to work out as 90,223 or something like that. But something that I maybe missed yesterday to specifically emphasize is that yes, we've used the lump system approach because I just want to do it to you as an illustration. But that doesn't mean it is valid. I've indicated that the Biot number shows that you cannot use it, and then our other criteria were also, it is only for small bodies and bodies with high thermal conductivity. So the lump system approach is a no. Okay, you cannot expect to get good results with a lump system approach. The second approach was still not perfect, which was a long cylinder approach, and that is to say that the dead body is a very long cylinder. Okay, very long, which means that the heat transfer rate through that area and that area would be negligible in terms of that of the total surface area. But at least it is a much better approximation than the lump system approach. Now today what we're going to do is we're going to do transient heat conduction in semi-infinite bodies. Now immediately if you see the word semi-infinite, you will ask, but what do they really mean? Now with a semi-infinite body means that it is a body which actually has a single plane surface. And I'm going to show it in terms of a coordinate system, like that. And in the x direction, that would be the x direction. And this body will have a plane surface, like this. And with that, I mean it's flat, or relatively flat. And then it is infinite in size in the x direction, as well as in the y direction and in the z direction. That's x, that's y, and z. So a semi-infinite body is firstly an idealized body. Okay. Then secondly, it has a single plane wall. Single plane wall. With that, I mean that surface area there. That is the single plane wall. Okay. And this body, or the surface, will originally be at a temperature Ti. And on the outside of this surface, we will have a temperature T infinite, as well as a heat transfer coefficient on the outside surface. And that surface temperature would be Ti at T equals 0. And the temperature of the rest of the body would be equal to Ti, and it would be constant for the rest of the body. So the third property of a semi-infinite solid is that the temperature change is close to the surface only. Okay. So the temperature of the rest of the body is not going to change. Okay, so the fourth one is that the rest of the body has no temperature change. Now, the next thing would be to try to answer, but which bodies are we now talking of? Typical good bodies or examples of semi-infinite solids would be, for example, the surface of the Earth, okay? Which, on a certain surface, and a certain place there will be a temperature change. So the temperature change will occur very close to the surface, but it wouldn't influence the rest of the surface. That would be a good example of a semi-infinite body. Another example might be you as a person, and you would say, but how can that be? It would be, again, our dead body, if I can show it as a cylinder. Okay? It would be the case where maybe a surgical procedure, or not a dead body, maybe a living person, but you want to do surgical treatment with a laser. And the laser is just for a split of a second, and it's on the surface of the skin, and there's temperature changes very, very close to the skin. Then the temperature of the rest of the body is not going to change, because if it does, it would be fatal. Also, maybe this wall. Again, if and the wall is very thick, maybe it's 300 or 600 millimeters. If the temperature in this room now suddenly changes from 25 to 0 degrees Celsius, and we want to know how does the temperature changes within the first few millimeters, and we only want to know it after 1 or 2 minutes, then this would also be an example of a semi-infinite solid. Because after 10 or 15 minutes, if this temperature goes back to 25, then the temperature in the rest of the wall is not going to change at all. So those are typical examples, and you always have to use your discretion in terms of when you can use the semi-infinite solid method. So you will see that when we do the work, I do not just give you the formulas. Okay. We sort of do the derivation, in many cases, not all the detail, but it is extremely important that you understand where it comes from, because that is the only way to ensure that you're going to apply it correctly. If you're just going to try to learn the formulas with problems and try to apply it, then you're going to make big mistakes. So it's very important that you understand the theory. So for that reason, let's look at where does it come from in terms of the solution of the semi-infinite solid. Again, it starts with the energy equation. The energy equation which says that ddx of k partial dt dx plus ddy partial k dt dy plus ddz partial k dt dz plus E gen is equal to rho c partial dt dt. The one T for temperature and the other T for time. And because this body is so big, the heat transfer rate, what happens here on the surface, suddenly the heat transfer rate will only be in one direction, in the x direction, because in the y and the z directions we've got an infinite surface on which the temperature change occurs. So it means that those two terms would be negligible. Again, it is a one-dimensional approach. It is an assumption that we make. And then we are also going to say that that term is equal to 0 because there's no chemical reaction on the inside, there's no nuclear reaction or anything like that. So the result is that we can write this as, and because k is a constant, we're going to say k is a constant, and for that reason we can say that the partial d2t dx squared is equal to rho c divided by k partial dt dt, or we can write it as 1 divided by alpha partial dt dt, alpha the thermal diffusivity. So again, it is the same equation as we previously had for the plane wall. Okay. However, the boundary conditions are different. The boundary conditions are different in the sense that firstly we're going to see, say as a first boundary condition 1, the temperature xt is equal to temperature where x is equal to 0, then the temperature is suddenly going to change to the surface temperature. So previously it was at Ti, and at T equals 0, the plane surface temperature changes to Ts. That's the first boundary condition. The second boundary condition is that, again, Txt is equal to T, and now where x is infinite, there the temperature is equal to Ti, our second boundary condition. And the third boundary condition is our initial condition, Txt, and that would be T, and now it would be at time 0. Time 0, temperature is Ti. And that's our three boundary conditions. However, we cannot do the separation of variables method in this case. It doesn't work because the body is infinite. That's the mathematical reason if you go and try to do it. And we have to use another method of changing the partial differential equation into an ordinary differential equation. So the partial differential equation, we have to change it to an ordinary differential equation. How do we do it? Well, with a trick, and that trick is to combine two variables into one single variable. And that single variable is equal to eta, where eta is defined as x divided by the square root of 4 times alpha t. So the two variables that we are referring to is x and t. So those two variables, when we put them together, now we have only one variable. And now it is much easier to change this partial differential equation into an ordinary differential equation. Let me show it to you also like there. So if you can just look there on the screen also, you can see a little bit more of the detail. Again, I'm not going to go into all the detail, but the result is that we now can write an ordinary differential equation as d2t d eta squared is equal to minus 2 times eta dt d eta, and that is equation 1. Okay. Now, with this equation and using this single new variable eta, we have to go and rewrite our boundary conditions 1, boundary conditions 2, and boundary conditions 3. Okay. And then you can solve it. And the result is an equation looking like this, T minus Ts divided by Ti minus Ts is equal to 2 times 2 divided by the square root of pi, the integral of 0 to eta e to the minus u squared du. And if you now wonder what is u, it is just a variable that you need, a dummy variable that you need to complete the integration with. Okay. So u is a dummy variable for integration. Now the result of this integration, there's not an exact integration for that. You have to do it numerically, and people who did that refer to that as the error function in eta. That the result is the error function in eta, and the error function can also be written as 1 minus the complementary error function, C. Not the error function, but the complementary error function. And this is equation 4.43 in your textbook. So there's no analytical solution for this integration. You have to go and do it numerically, and the result is given in table 4.4 in your textbook. So the result is of a numerical integration. Let's look at it quickly. In table 4.4. And that is the result there. On the left, you will also see a graph of the error function as a function of eta, so that is how it looks like. Table 4.4 gives typical values of eta, and then it gives the complementary value. Not the value, the error function, but the complementary one, this one here. So if you look in table 4.4, you will see different values of eta and then values for the complementary error function, like that. And look, if you agree with me, you'll see that typically if eta is equal to 0, then that value is equal to 1. Okay? If eta is equal to 1, then it is equal to 0.1573. Okay, if it is equal to 2, it is 0.00468. And it's very important to observe what is happening now with this value, because when you get to 3.6, then it is already 0 for 5 digits, very small. So look at the graph also. If you look at the graph, you will see what happens with the error function itself. At 3, it starts becoming 1. That's the error function, not the complementary error function. So the complementary error function is 1 minus 1, and therefore you can see the value approaches the error. Complementary error function approaches 0. Okay. So this is an important observation. And if you take notice of this, it can save you a lot of time in the test and exam, because there were many such problems in previous tests and exams where if you took note of this, it would really save you a lot of time. And I'm going to do an example like that a little bit later. What is important, however, is to realize that the specific boundary conditions that we have used, that boundary condition 1, boundary condition 2, and initial condition, and yes, we did write them in a different format, but the result of those boundary conditions gives this answer. Okay. Now, there are other types of boundary conditions that may be used. For example, you could have specified that at T equals 0, this temperature is not constant, but you've got a constant heat flux, maybe a solar radiation on the surface, but you do not know what the temperature is. That can be a different boundary condition. Or another boundary condition can be, on the surface you've got a cold stream of fluid with a certain heat transfer coefficient. That would be another type of boundary condition. Therefore, in this part of the textbook are summarized 4 case studies with different boundary conditions. And I'm going to show them like this schematically. So the first one, okay, now remember, in this dimension it's infinite and that dimension is infinite. So the case 1 boundary condition is where that temperature is specified as Ts. That's the one that we've done just now. The second type of boundary condition, is where the heat flux is constant. The heat flux. Remember, small q is the number of watts per square meter. Okay, the number of watts per square meter. So maybe it is solar radiation, and it can be maybe 700 watts per square meter on a flat surface. The third type of boundary condition is where over the surface at T equals 0, we've got a fluid stream at a certain temperature and a heat transfer coefficient. That's the third type of boundary condition. And the fourth type of boundary condition is, for example, when you have a laser. And with a laser, we have a pulse E, which is going to transfer a certain number of joules per square meter. So normally the square meters is very small, and you've got an energy pulse just on a surface for small period of time, normally less than a second. So those are the 4 types of boundary conditions. And all of them would give different solutions in terms of the error function. Some more complicated, some easier. And those are summarized in your textbook, and they are summarized as equations 4.45 to 4.48. And let me show them to you, how they look like. There they are. All 4 of them, case 1, case 2, case 3, case 4. For case 1, the specified surface temperature Ts, we didn't do it, but it is in the textbook. You can also solve the heat flux on the surface there, and there's a formula for that. Case study 2, the heat flux on the surface is constant. Case study 3, convection on the surface, that long one. And then case study 4, the energy pulse. So if you look at that, you'll see the case study 3 is actually the one that looks more complicated and looks like as if it is much more work to solve than the other equations. Do you agree? Okay. So for that reason, let's do such an example. Since it looks so complicated. So the example would be over the surface of the Earth. Okay, the surface of the Earth. And the surface of the Earth is originally at a temperature of 10 degrees Celsius. 10 degrees for the first few meters. Okay? Not a few hundred meters, just for the first few meters. And the thermal conductivity of the ground would be equal to 0.9 watts per meter Kelvin. And the thermal diffusivity is equal to 1.6 multiplied by 10 to the minus 5 square meters per second. And at T equals 0, we've got a cold wind with a heat transfer coefficient of 40 watts per square meter degree Celsius, and with a temperature of minus 10 degrees Celsius. So at T equals 0, we've got the cold wind blowing over the surface. That is the heat transfer coefficient, and that's the temperature. What we want to know is that at a depth of half a meter, 500 millimeters, from the surface, what will the temperature be so that is where X is equal to 0.5, and that is what will the temperature be after 10 hours. Do you all understand the problem? So we've got the Earth originally at 10 degrees Celsius for the first few meters. Thermal conductivity is 0.9. Alpha, 1.6 multiplied by 10 to the minus 5. At T equals 0, so at T equals 0, the wind would start blowing over the surface. The heat transfer coefficient is 40, and the wind temperature is minus 10 degrees Celsius. Question is, at a depth of 500 millimeters, what will the temperature be? Is this just a theoretical problem, or are there any practical solutions? Yes, there are many practical solutions for it. Normally surfaces like water underneath the surface, we would like to know if it's going to freeze or not. So therefore you want to make sure that the depth is deep enough so that that doesn't happen. In some cases, chemicals are being transported, power lines, etc. Many applications where you would like to know underneath the surface of the Earth, what will the temperature be as a function of time? Okay. So this is a classical example of a semi-infinite solid. It is close to the Earth, half a meter, if you take that in comparison with the diameter of the Earth. Very close. Okay. Originally it's at the stable temperature, now suddenly we've got the wind flowing over it. If we look at the 4 different case studies, Cameron, if you can just show it to us again, then the obvious one that we want to solve is case study 3, isn't it? It gives the heat transfer coefficient and the temperature of the wind flowing over the surface. So it is unfortunately this long equation. And this long equation says, okay, so let's first say, just make sure that you all understand, so we are referring to case study 3. So that case study says the temperature as function of time minus Ti divided by T infinite minus Ti is equal to the complementary error function of X divided by 2 times the square root of alpha T minus the exponent of Hx divided by K plus H square alpha T divided by K square multiplied by the complementary error function of X divided by 2 times alpha T plus the heat transfer coefficient multiplied by the square root of alpha T divided by K. Long equation. Okay. In the test and exam, what is the best approach to try to solve something like that? Well, the best approach is normally to take these things and break it up into smaller terms, look at them on a basis of a term-by-term approach. However, once you've started doing many of these, you will actually realize that you actually have the complementary error function of something. Okay? And if we go back to what I've showed you previously in table 4.4, if eta is typically larger than 3.6, then the complementary error function would go to 0. Okay. So if this is more than 3.6, that would be 0, and then you're going to have 0 multiplied by that, and then you can end up with one term. Okay, isn't it? So that is exactly what now happens. So let's just look at that term. First, x divided by 2 times alpha t. X would be equal to 0.5 divided by 2 times the square root of alpha, 1.6 multiplied by 10 to the minus 5 multiplied by 10 hours of 3,600 seconds. 10 hours, 3,600 seconds in an hour, and that would be the value of x. And the result of that is equal to 0.3214. Okay, so that term is equal to 0.3214. Let's jump to that term there. The heat transfer coefficient multiplied by alpha t divided by k. The heat transfer coefficient is 40. Alpha is equal to 1.6 multiplied by 10 to the minus 5. The time t is 10 hours of 3,600 seconds divided by the thermal conductivity of the ground, of the earth, is 0.9. And the result of that is equal to 30.36. That's so if we look at this term here, then the result of that is equal to 0.3214. The result of that term is equal to 30.36. And those two together is by far larger than this value of 3.6. Okay? Therefore, this term is equal to 0. 0 multiplied by that means that this whole term now is going to disappear. Don't have to calculate it. And the result ends up as a very simple case up to there, which already we've solved. So we've actually already solved that the temperature xt minus Ti divided by T infinite minus Ti is equal to the complementary error function of x divided by 2 times alpha t. And this is equal to, well, let's do the substitution here. We want to know the temperature as function of time minus the initial temperature of the Earth is 10 divided by the temperature of the wind of the stream is minus 10 minus the initial temperature is equal to 10 is equal to the complementary error function of 0.3214. If you can look in table 4.4, where eta is equal to 0.32 approximately, you'll see that the complementary error function is then equal to 0.6509. Do you agree? The complementary error function, where eta is equal to 0.3214, in the table is equal to about 0.6509. So the only unknown is now the temperature as function of time, which we can now solve, and it means that the temperature, where x is equal to 0.5, and after 10 hours is equal to -3 degrees Celsius. Okay. Any questions, ladies and gentlemen? Yep.
The exponent, does it include that whole bracket? No.
Yes, it is the exponent of, it is the exponent of this multiplied by the error function of that. Yeah. You see, yeah. Yeah. So it's the exponent of everything there multiplied by that, and that is now equal to 0. So it is 0 multiplied by that. It's all equal to 0. Okay. So be careful in the test and in the exam that you do not just start crunching through all the calculations. It can really save you a lot of time and make things much simpler. Any questions, ladies and gentlemen? If not, thank you. That's the end of the lecture.